John here. Sometimes you just need a hard copy. And very much so you needed them back in around 1980 because if you had a terminal at all, it was usually 25 by 80 and kind of on your desk. And, you know, if you really wanted to look at something, you need more than a few lines of code. You wanted to print it out, take it to the kitchen table with a cup of coffee or something. Anyway, printer ports were very important back in those days. Okay, so quick recap. Here's how the printer port works on the Z80 Retro board. The pinout on this connector is set up so you can just press insulation displacement connector onto a ribbon with a DB25, and the pins come out to be compatible with the standard PC parallel port. And therefore, you can buy an adapter for any printer known to man that was capable of talking to an IBM PC. So that's why I chose this particular pinout. The bottom line is it's a parallel device. You send 8 bits at a time to tell it what character to print. There's a signal called strobe up here on pin 1 that goes low and then back high once for every character that you want to send to the printer. The printer responds with a busy signal. Whenever this is low, it means don't send me any more bytes. They'll be thrown away by the printer. So the algorithm that I wrote, my driver for this, is basically wait until busy is high. When it's high, you can then update the 1 byte value on these 8 bits here, and then take the strobe low and then bring it back high again after a while. Now, if you want to know, you can, ask, is it out of paper? That's what the paper signal's for. And you can ask if it has an error condition or something like that, okay? Some printers know if they're jammed or not and all this other fun stuff. And that's what these other signals are pretty much related to. There's a line feed signal that means every time the printer is asked to move the carriage back to the left, if this is low, it should automatically also advance to the next line. That's not needed on any software that I particularly like to use. So this, for me, I always set it to high. And the same thing for the initialization signal here. If you reboot your retro board, you probably want to cycle this low and then back high again. That's what the IBM PC used to do, which is why if you ever reboot a PC and you have a printer plugged in the parallel port, you hear the printer go nuts to reset itself and realign its head and all that other fun stuff. I don't do that, at least in the versions of the code that I'm using now. So I just leave these alone and ignore them. But by hooking them up like this, we have the ability to tinker with them if we so desire. In this design, this is the schematic for the revision 4 version of the retro board. The only difference between the 3 and the 4 is that those two signals come down here to different pins. They're actually hooked up to the SIO chip because I ran out of bits on the regular parallel ports in this design. And this is also very common back in the day. To save every last penny on a machine, you would use otherwise pins that you would otherwise not have a reason to connect to anything, which are the handshaking lines on the SIO. So I hook them up to the handshaking lines that are otherwise not used in the design because these are output bits, and I can manipulate them to set them high or low on demand. So that's very convenient. Now, the difference between the 3 and the 4 is this line here, which is the line feed signal, okay, that comes around here, is connected up to DTR on port B of the SIO. Okay, it used to be in revision 3 hooked up to RTSA. Now, if you pour through the dock on the SIO, this was a bad choice because the RTS pin is not a general purpose output pin like the DTR lines are. Okay, so by using DTRA and DTRB for this, these pins, depending on how you configure the SIO, are under total software control and otherwise don't have anything to do with the serial port, okay? Now, it turns out that when you reboot the SIO and you cycle the reset signal here, right, when reset goes low, the SIO sets both of these pins high. So by default, I can just completely ignore them, all right? When those are high, it comes around here, and then My point is that neither the line feed nor the init signal will be low, and that's the normal operating mode of a parallel printer port. So we can focus on the data, the strobe, the busy signal. And for now, I'm going to ignore the paper empty and the acknowledgement and stuff like that. You can play around with that if you want. I'll leave that as a task to the viewer. So how does this thing work? If you look over here, there's the printer data port. Okay, well, this is an 8-bit latch. We write to I/O port number 20, send any data value we want, and that will set the data lines accordingly. Okay, now how do we read the status? All right, here's the busy signal right here. Comes in on bit data on the data bus bit number 3 whenever we read from this input port, which is connected up over here to I/O port number 0. Okay, so we can look at the busy signal, and we can look at, paper empty and stuff like that. All we really care about is it busy or not, for the simple tests that I want to run. Okay, so we can read from the general purpose input port until busy is high, indicating it's no longer busy. When that's true, we can come down here, we can put a data byte on the data bus, send it out to the printer. Once we've got the data on the data bus, how do we cycle the strobe? Well, we go over here to the general purpose output port on I/O port number 10. We can set this bit low. Over here, you can see it's connected up to D3 on the data bus, and then set it back high again a little bit later. And that'll tell the printer to take the data byte that we put on here and print it. Okay? Now, there is one issue that comes up here. Unlike this port up here, that anytime I want to, I can just read from this latch and see what all these values are. And by reading it, there are no side effects. And by that, I mean, reading this doesn't cause me to, reset any of these bits or anything. Okay? You just read it, you're looking at the current values of these pins, these bits over here, and there's nothing that will acknowledge or be changed as a result of looking at this. Okay? Now, on this output port over here, we have a bit of a problem. There's no way to just set the strobe only this one bit. I can only set all the bits at once. If I want to do anything at all, I have to set the value on every one of these pins. Right? Now, this is a kind of an annoying misfeature of this design, but there's software ways around dealing with this when it gets ugly. So what else is on here? Well, these are all the control lines for the SD card. It would be nice not to accidentally erase our SD card or otherwise screw it up while we're trying to print something. Another thing that's very important, you can never change the bank number here unless you really want to. You have to be very careful not to do this at the wrong time, or it's an instant one-way trip to crashing. Okay? So every time we update this strobe signal, we need to be very careful not to disrupt whatever value is currently on the SD card bits and the low bank select bits. Okay? Now, we can kind of hard code these while testing the printer port if we want to, but you need to come up with a technique to make sure that your code doesn't accidentally change these other bits while diddling with the strobe signal, and vice versa. When you're talking to the SD card, you don't want to accidentally be printing garbage, okay? So along with other things, let's look at a simple way to make sure that we don't accidentally change these when we don't want to, when we put together our little test code, all right? So here's the test code for the Z80 Retro board and the tests directory that comes from the GitHub account for the board itself. So here's the Align Printer test program. And it starts out like all the other test programs. We set the stack to 0 and let it wrap around to the high order address. What we're going to do is we're going to copy all the flash data into the static RAM, initialize our stack pointer, and then go on our merry way and run our program. This is a really simple one. We're going to initialize the serial port. We're going to initialize the printer port. And then what are we going to do? We're going to say load HL with some message label, which is right here. So we're going to take HL and load the address of this text string in here. We're going to load the BC register with a number of bytes in that message. I talked about this before. This technique of saying $- minus, some label that comes up here, that will equate to the number of bytes in these storage areas that are defined with the db command. Now, whenever you put double quotes around a text string in this assembler, what you'll end up with is just the ASCII codes, 1 byte for each one of these letters. And a \r is the return, \n is a new line. So if you want to move the head to the left, that's the R, \r. You want to go down a line, that's \n. You can leave the \n off if, in your design, you configure the signal on this pin here, the line feed, to be 0. That's what this is for. Am I going to be responsible for saying return and go to the new line when I send my data to the printer? Or am I only going to do a return and let the printer decide to go to a new line? Okay? The problem with taking the option of making your life easier by leaving the new line out is that you cannot go back and overstrike a line. If that's what you want to be able to do, you just forfeited that as an option. I'm just saying. Okay, so what are we doing? We take the number of bytes that we want to print and put it in BC, and then we call this thing called print stir. And then we go into this halt loop down here. We've seen this before. This stops the Z80 if it ever wakes up. The only reason it would wake up is it got an interrupt or something like that. It'll just go back and halt again, okay? So let's look at we've already seen this. I talked about that in another video on how to test and verify the SIO port. SIO-A is the console port. I don't even think we print anything to the console in this app, by the way, so this is somewhat superfluous. The line printer init, is that down here, or there's an LPT ASM file for that? Okay, great. So let's look at the line printer init and the print stir, which is down here. I guess we can talk about the print stir while we're on this file. What does this thing do? It's going to write the BC number of bytes from memory, whose address is in the HL register, because that's what you saw up here a second ago. What are we going to do? We're going to save the BC register so we can get it back down here, decrement it by 1, ask if it became equal to 0. I mentioned this technique in the SIO video. And if it's not 0, go back up here and keep going. So what happens up here? Okay, so we load the character from memory at the address that's in the HL register. We call line printer transmit. This is where we increment the HL register to point to the next byte. So the first time it'll put H, then E, then LL, because we're advancing the HL register. Okay, and then of course the pop in, check of 0, and go on. When BC becomes 0, we return from print string, and that's when we fall into the halt loop. So the only thing left then is the line printer init and the line printer transmit routine. And that's in the line printer ASM file here. So what do we do when we initialize the line printer? We grab a byte from memory at this label. This is the thing that remembers the other bits. When I was talking about the need to make sure that we don't disrupt the current setting on the low bank and the SD card when we're diddling with the strobe signal here. Okay? That we're going to create a byte in memory, and we're going to store the current value that's in that latch. And we're going to keep a copy of it. We're going to keep a cached copy of the last thing we write into that latch, okay? We need to do this because in the design of the board, there's no way to read this. The Z80 can't read ask, hey, what is the current value here? So I can then change this 1 bit and then write it back into this port, all right? There's just no way to do that due to the simplicity of the design. Yes, if we used a PIO chip, sure, you would have that kind of functionality. But in order to save PC board real estate, because the PIO is a giant chip compared to this little tiny one here, this is a sacrifice that I decided to make when I did the design. So in other words, we just have to keep track of it on our own. So we'll see where that is. It's in the print test routine. You saw it briefly on the screen when I was scrolling around before. We'll look more closely at it in a minute. Anyway, so what we're going to do is say, tell me the current value that's in that latch chip. I'm going to OR one of the bits to make it high. And this is part of the io.asm file that we include in the main routine. So in here, I enumerate all these bits. So here's the print strobe bit. It's 8 in hex, right? Well, that's 8 in hex because what do you got? There's 1, 2, 4, 8. Okay, so this bit, if this is a 1 and all the other bits here are zeros, the value in hex would be 8. Okay, so that's how these things all work. So if I say or the current value in the cache with an 08 in hex, then what I've done, as I've said, make sure that the print strobe bit in the accumulator is high, along with whatever else was there before. Then I'm going to replace the value in the cache with that new value. In addition to that, I'm going to output it to the GPIO output port, which is going to be on whatever this is, port 10. Okay. Again, this label, this symbol would be defined in io.asm. And I'm sure there it is, GPIO printer data, or rather the GPIO out here is in fact at IO port address number 10. Okay. So that's where these things come from, and that's what they're for. Let's take a look and see where I define the cache value. I put it at the bottom of this file here. See this? So this is the main program I'm running. Somewhere, something has to define a byte with this label so that that printer driver in lpt.asm and SIO and any other thing that needs to know what that value is can get access to it. Now I initialize it like this. Now it turns out that I do initialize it with the print strobe set to 1, but I went ahead and wrote a formal initialization routine for the printer, presumably, so I could recall it again later and make sure that it is in a known configured state, regardless of the current value of the cache. So in the end, it just makes sure that that's a 1. Okay, that's all it does when I initialize. In a more sophisticated system, it might reach over to the SIO and configure the SIO to make sure that these two pins here are also 1s, so that these signals I talked about before are both high. Okay. Or even more sophisticated, it might even toggle this low and then back high to reset the printer. Okay, we can make this as fancy as we want. Right now, keep it simple. Okay, so that was the initialization logic. Then there's the printer transmit routine down here. So how does this thing work? It calls LPT ready, and we just saw that scroll by. It's right here. LPT ready reads from the GPIO input port, which is the 244 we talked about a minute ago. We need to see the busy bit right here, right? So this is going to read from port number 0 over here. And I'm going to do an AND command to see if this bit is on and ignore the rest. So I'm going to say AND it with pern busy. And we saw that a minute ago in the IOASM file. So read the port and the accumulator, which is where I put the value from the port, with this value here. And if the result is 0, the Z flag will be set. If the result is non-zero, the Z flag will not be set. Okay? Plus the A will also be 0 and so on. So when this thing is done, if the accumulator is 0 and the Z flag is set, and or the Z flag is set, then the printer is ready to go. Otherwise, it's not ready. So this thing here says call that, and it comes back. And if the accumulator and the 0 flag is not, if we have a non-zero status coming back, just stay there forever waiting for the printer to become ready. Okay. Then what do? We load A with C. Well, it turns out this is going to print the character that's in the C register when this thing is called, okay? So I need to put it in the accumulator so that I can output it on the printer data port, because I cannot write the C register out to this port, because the output command only lets me to output the accumulator, okay? It's the price you pay when you're trying to save money designing a CPU. So pern dat is going to be the IO port number for the printer port. in the IOASM file. Then what are we going to do? We're going to insert the strobe signal. So we go back to the cache here. Now look what happens in here. We have to be very careful about what's happening here. We're going to grab a copy of the current cache value. We know, because we already initialized it, that the bit for the print strobe is currently high when we get in here. What are we going to do? We're going to AND it with tilde print strobe. This is a ones complement operator. So that basically says take the print strobe value, which is that hex 80, I think, right? The print strobe, that's this guy down here. Or I meant 08 in hex, 08, okay? And when you put tilde in front of it, what you're doing is you're inverting every one of those bits. So you're going to end up with an F7. So if I AND the accumulator with an F7, what it does is it leaves every bit alone except this one here, the print strobe bit, and it forces that one bit to be 0 while not touching anything else in the accumulator, all right? So I'm going to turn this one off, and I'm going to output that on the GPIO port, okay? And I note here I did not save this. I didn't replace it in the cache, okay? And the reason I didn't do that in this code here is because later on, I'm going to just simply set it back to the way it was, which was to make the bit for the strobe bit go high again. So I'm going to read the cache, make sure the strobe is 0, output that. Now the printer strobe bit is active, low. I'm going to waste a little bit of time. I'm going to count to 10. Load A with 10, decrement it by 1. If it did not reach 0, go back up to the wait. When it's done with that, it falls down here. I grab the cache copy, which gives me the one, the copy that has the strobe bit high again, like it was up here. I'll put that in. I'm done. All right? That's all we need to do to print. So a quick recap on what are we printing. So this program is going to say hello from the printer, go back to left, go down a line. There's a test, make sure the new line works in a sane manner, go back to the left, and then go back down. Then it's going to go into a halt loop. So that's all we're going to do in this test app. So let's make it go. We're in the README file. There's a little message on how to program the firmware, like so. And we want to put in there the printer. Oh, we got to assemble it first. Put in the printer program, which is going to be LPT1. When we're done assembling, where is it? LPT1 hello or whatever .bin. There's a CTC. It's right there. That's SIO. Boy, here it is. Good luck finding it in all that mess. Now we go over to the printer and try it out. Now I kept the printer offline before I rebooted the Z80 because I wanted to make sure that I could film this. I only have so many hands. So I'm going to put it online and we should see it go. If you're going to have a printer, you have to make banners. So here's a variant of the printer test program. No changes in here at all other than the stuff that I'm going to print out. Now, all I've done here is I'm going to print this thing here, then I'm going to print my waste paper routine, which is going to be a loop that just continuously prints a message, okay? So what the heck is RX80 compress? So what we got here is 2 messages. Here's the label, and here's the length. It's the same game I played with all the other ones. It turns out this is only 1 byte, whose value is 15 in decimal or 0f in hex. If you send that to an Epson RX80, it puts it in what we call compressed mode, which makes the printing characters narrower than usual. So you can fit 132 columns per letter sheet versus only 80, okay? So this puts it in 132 column mode, and then down here, waste paper is the same thing we saw before, except it's in a loop. Grab the message, grab the length, and then call the print string, same as before, and then just go back up and keep wasting paper. So I've got a couple of different routines in here. Let me shrinkify the font on the screen so we can sort of see what's going on here. So these are the messages. You know, you either want to say, hey, retro print test or whatever, and or you want like the hollow letters like this. I got these from an application called Figlet. Google it, Figlet. Have fun. It's a good waste of 4 hours of playing around and finding fonts if you're into that sort of thing. So I have an if 1 here on this section of data, or an if 0 and another if 0 here. I just pick one of 3 different banners. If you look closely, this third one is a message that says mostly overstrike, so that I can exercise the print carriage without wasting so much paper. So what this thing actually does is it prints this whole thing over itself, because we only go carriage return without the new line here. And in the end, I do a carriage return and a new line. So the idea is, when I first fired up this printer that hasn't been used in 20 years, the head didn't want to move around as nicely as it used to, and I put a very thin layer of, I don't know, like mineral oil or something on the rods and stuff, just to exercise it, to get the thing to move around. So anyway, using this message, it does print, but only prints one line in spite of all this, while moving the head back and forth like crazy, just to exercise things. This, of course, will just print this out over and over again like that. The one up here will print the hollow message. So pick whatever you want, have fun. Go ahead and program that one up. So make sure everything's compiled. Print out the banner by loading this into the flash memory. And voila, it's like 1983 all over again. Thanks for watching. I'll see you next time.